Okay, so today is a big one. We're talking about the end of a mathematical story that's been unfolding for nearly a decade. This isn't just another paper in a long line of them. This is the one that lands the final decisive blow. This is how a conditional what-if proof finally became an unconditional, rock-solid theorem. That's right. I mean, this whole thing kicked off way back in paper 26. That's where we met the main characters, the bird map itself, and these two different ways of looking at it, the orbit ladders and the Watson ladders. And the hint, the thing that got everyone excited, was that these two behaviors seem to live in completely separate bands. Now, paper 34 got us right to the edge of proving it, but it left us with this huge cliffhanger, a massive if. The whole thing worked if two big assumptions were true. Well, paper 35 is all about getting rid of that if. Exactly. So that's the central question for us today. How do you knock down those last two dominoes? In this explainer, we're going to unpack the really elegant solutions to those final questions. We're going to see how a very promising hypothesis was hammered into a cold, hard mathematical fact. Let's dive in. All right, so here's our roadmap. First, we'll quickly recap those two open questions that left us hanging. Then, we'll tackle the solutions one by one. First, building something called the pressure bridge, and then certifying the spectral gap. We'll also see why a third theorem was needed to really lock it all down. And then, we'll get to the big reveal, the unconditional theorem itself. And of course, we'll wrap up by looking at what's next. Okay, let's get into the nitty-gritty. You see, paper 34 was a fantastic piece of work, but it came with this one major string attached. It proved Watson-van rigidity, but only if two other things were true. So the entire mission of paper 35 was to cut that string and make the proof stand on its own 2 feet. So here they are, the two missing puzzle pieces. First up was the spectral gap. You can kind of think of this like the space between a guitar string's main note and all its overtones. You need that gap to know you have a clear, dominant behavior, something stable that isn't just lost in the noise. The second thing was this pressure bridge, a hypothesized connection between two very different ways of looking at the system. Both were absolutely critical, and both were still just, well, hypotheses. All right, let's tackle the first problem, building this pressure bridge. It's a great name, but what does it actually mean? What two different mathematical ideas is it connecting? So this is where it gets really cool. It connects two worlds that seem totally separate. On one side, you've got rho. That number describes the growth rate of the system's orbits. It's a very physical, geometric idea. On the other side, you have r, the spectral radius of an operator, which is this abstract beast from functional analysis. The pressure bridge is the wild claim that these two numbers, coming from completely different angles, are actually the exact same thing. And the proof itself is just beautiful. The masterstroke is in step 1. They cleverly redefine the ladder coefficients. Instead of using orbit sums, they use an integral that has the transfer operator baked right into it. That's the key that unlocks everything. Once you do that, you can bring in the big guns, the Ruelle-Perron-Frobenius theorem, to nail down the growth rate. The final step is just a classic formula that connects that growth rate to the spectral radius. And bam, the bridge is built. But, and this is a big but, there is a hidden danger. The specific numerical technique they used to actually calculate that growth rates, well, it had a potential flaw. There could have been a tiny, subtle error introduced by the method itself, a little gremlin in the machinery. An error so small you'd never see it in a simulation, but just big enough to make the formal proof fall apart. The whole thing was teetering right here. And this, for me, is the emotional peak of the paper. Lemma 2.3 is the hero. It proves rigorously that this potential error, that gremlin, actually shrinks so fast that it becomes completely irrelevant. It literally vanishes faster than the thing you're trying to measure. This is where they flagged the one spot the argument could break and then proved beyond a shadow of a doubt that it was safe. It's the moment a hunch becomes a certainty. The bridge holds.
Okay, 1 down, 1 to go. The pressure bridge is solid. Now it's time to deal with that second open question, the spectral gap. But notice the wording. The paper doesn't just say there's a gap. It says it's a certified gap. So what's the difference? What does it actually mean to certify a proof?
You know, it's really the difference between hoping you're right and knowing you're right. A regular computer calculation uses floating point numbers. They're fast, but they have these tiny rounding errors. You just have to hope they don't add up and spoil your result. A certified proof, on the other hand, uses something called interval arithmetic. Instead of one number, it gives you a range, a minimum and a maximum, and it guarantees the true answer is somewhere inside that range. There's no guesswork. It's a proof. So to make this absolutely airtight, they did this really clever 2-stage check. First, They built this massive matrix to get a really good estimate of the gap, kind of like a quick, powerful first draft. But then, and this is the critical part, they did it again on a smaller scale, but this time using super high precision, 30-digit interval math. This second check was to make absolutely sure the first result wasn't some weird numerical fluke.
And this table really says it all. Don't worry about the individual numbers too much. Just look at that last column, the certified gap. These values aren't just, barely positive. They are huge. It's an unambiguous, decisive result. This isn't a close call. It's a total knockout. So here's the bottom line. At the end of the day, the smallest certified gap they found was still over 290. This wasn't some borderline case that could go either way. It was a decisive, non-zero result. The existence of the spectral gap was no longer a hypothesis. It was now a computationally verified fact. Hypothesis number 2, closed.
Okay, so the bridge is built. The gap is certified. It really feels like we should be done, right? We're at the finish line. But then there's this third theorem, Theorem C. So why? What else could there possibly be left to prove?
Well, the issue is that Theorem B gave us rock-solid proof, but only at a few specific points, like islands of certainty. We knew it was true at epsilon equals 0.84 and at 0.9 and so on. But for the main result, we need to know the gap exists everywhere in between. Theorem C is what builds the bridges between those islands. It uses a powerful tool called the Keller-Liverani theorem, which acts like an insurance policy. It guarantees that if something like a spectral gap exists at one point, it has to exist in a whole neighborhood around it too.
And they actually calculated the size of that neighborhood. They proved that the result is guaranteed to hold for a stretch of at least 0.06. Now that might not sound like a lot, but it was more than enough to connect their islands of certainty into one continuous, unbroken stretch of proof. Now finally, all the pieces were in place.
And that brings us to the moment we've all been waiting for. This is the payoff. This is where all those individual theorems and lemmas come together to give us the final, beautiful result. So let's just run down the checklist. The pressure bridge connecting the two worlds, check, that's solid, thanks to Theorem A. The crucial spectral gap, check, certified and huge, thanks to Theorem B. And does the proof work everywhere we need it to, not just at a few points? Check, that was Theorem C. Every single open question from paper 34 has been answered.
And here it is, the unconditional theorem. For any parameter you pick in that key range, the Watson ladders are guaranteed to fall within that specific Watson band. And since we already know where the orbit band is, this proves it, once and for all. The two bands do not overlap. They are provably, rigorously, and unconditionally separate.
This is the last sentence of the proof in the paper. It's so simple, so understated, but it carries the entire weight of a decade of hard work. After almost 10 papers, what started as just a curious observation on a computer is now, finally, a theorem. That sentence has been earned. But you know how it goes in math. The second you answer one big question, it just opens the door to the next one. So now that this long journey is over, what happens next? Where do we go from here? The next big frontier is the question of universality. This entire incredible proof was for one very specific function, the WBA kernel. But there's a whole family of functions that look and act a lot like it. So is this weirdly rigid separation of bands something unique to this one special case? Or is it a universal law that applies to all of them? That is the huge question that paper 36 is going to try and answer.